Hey everybody, guess we can get started. Welcome to the third and final public observing event of this semester, Multi-Wavelength Astronomy. We have a really exciting night planned. And yeah, why don't we start? We're waiting for one more person who's at the observatory who will be joining us shortly. But in the meantime, why don't we just start with some brief introductions? My name is James Garland. I use he, him pronouns. I am a junior astrophysics major at Haverford. And tonight I will be doing a little fun quiz activity with everybody.
Hi, everyone. I'm Kate. I'm a student at Bryn Mawr. I'm a senior this year. And so I'm happy to be here. This is always very fun. If you ever want to access this later on, it's available on YouTube. And this is our last event of the semester, but there'll be plenty more next year and in the fall. And we hope that you join those as well.
Hi, everybody. My name is Sam Berry. I use she, her pronouns. I'm a junior at Bryn Mawr College, and I'm studying physics and some astronomy. And I'll be doing a little talk today on how our eyes compare to telescopes.
Hello, everyone. I'm Karen Masters. I use she, her pronouns. I'm a professor of astronomy and physics here at Haverford College, and I'm going to mostly be in the background this evening.
Hi, everyone. I'm the guest speaker for today. I'm currently a visiting assistant professor at Haverford College at the Physics and Astronomy Department. So my name is Natalia, and I'm very happy to talk with you about multi-wavelength astronomy today.
Great. All right. Well, I think we'll see if our call in from the observatory comes in when we get to that section. But without further ado, why don't we start with Natalia's talk?
Okay, thank you. So let me share my screen. Can everyone see my screen?
Yes.
Oh, whoop, 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 whoop. What's that? Okay. Okay, I'm doing this for the first time with this thing, so. Okay, let's do this via my beloved PDF. It's working better this way. Alrighty. Okay, so welcome to my short talk today, which will be focusing on multi-wavelength astronomy and also a little bit of astrophysics. So what you see here in the background is actually a galaxy, Centaurus A. And as you notice, there are kind of like different colors in this picture because this picture is actually not one, but several, all of the three that you see here to the side. So an optical picture, a radio picture, and an X-ray picture, and they have been all overlapped and summed up to this one fabulous picture, I think. So this is a galaxy that has a very weird shape. So we see basically like some structures here. We see radio emission here. This is the kind of like magenta form of emission. But this picture shows you very well why we are actually doing multi-wavelength astronomy, because we can just learn a little bit more about these sources and what kind of emission they generate and what makes them work. So just to give you like an intro, why multi-wavelength astronomy is not only beautiful when you look at pictures, but also necessary for us as astronomers to actually understand what how different sources in the universe look and work, like how they generate their emission. So a little bit about me. As I just said, I'm a visiting assistant professor of physics and astronomy at the department. I'm also a radio astronomer, and as a radio astronomer, I do lots of multi-wavelength studies during which I also dig into other wavelength ranges like gamma ray astronomy or X-ray astronomy. So these are some of the telescopes with which I observe. This is the Green Bank telescope, the former Arecibo radio telescope, and the Very Large Array. So I observed with all of them, and I must say that it's always a great experience to carry out observations. So if you ever have the opportunity to watch or to be there while observations are being carried out, I recommend to actually try that, because it's a lot of fun. So what is the purpose of multi-wavelength or MWL astronomy and astrophysics? Well, I did not put anything on this slide because I believe that pictures speak more than and better for themselves than just words. So this is one galaxy which we refer to as M94 or NGC 4736. And similar as in the title slide for this talk, you see that also this galaxy has several different colors. And whenever you see a picture that is beautiful and has like different colors in it, you can assume it was taken with maybe different filters, maybe different instruments, and kind of like overlapped. So we have like summed up picture of it. So this is a beautiful spiral galaxy as we see, and we see like spiral arms. We see reddish areas, which are star forming regions. We also see like these bluish stars in the foreground. And this is a very cool picture when you just look at the optical side of things. But when you actually start observing the very same galaxy at other wavelengths like infrared and ultraviolet and make a so-called composite, which is such a combined picture of all of these pictures here to the right, you see that you see way more details than just in the optical picture. So for instance, you can see these spiral arms much more pronounced, better. You see how they actually, you can follow their trace. You can see star forming regions as well. You can see different densities of gas. So we usually combine pictures taken at different wavelengths because we really want to learn how such a source generates the light that we see from it. And when we speak about light, we don't only mean optical light, but we also mean like infrared light, different wavelengths, and ultraviolet light. So just as a hint why we actually are doing that. So when we do multi-wavelength astronomy, we actually move in different parts of the spectrum, and that's just a sketch of the electromagnetic spectrum. So all kinds of light that we are aware of. And as you see, the visible light is actually just in this very small wavelength range, covering all of these colors. So what we actually see with our eyes is just like a tiny part of the electromagnetic emission. All of the other wavelengths here, like ultraviolet, X-rays, gamma rays, are not visible to us by just looking at sources. So we need telescopes for that. Actually, an interesting fun fact is that cats can actually see a little bit into the ultraviolet range because they have slightly different eyes than we do. So they can also see UV light. But yeah, so when we talk about multi-wavelength astronomy, we actually move through this whole spectrum, really from radio waves, microwaves, infrared emission, including visible, so optical wavelengths, ultraviolet, X-rays, and gamma rays. So we use everything. And something that I have been also teaching some of my students during this semester, that's almost over, is actually multi-wavelength emission from different sources in the sky. One good example was Jupiter. And we all know these beautiful pictures of Jupiter that we see here taken with the Hubble Space Telescope that is actually over 30 years old now, but it's still working great. So what you can see on Jupiter's surface is lots of interesting clouds with different shapes and patterns. And you also see this kind of like great red spot that has been observed for the past several hundreds of years. It was discovered by Galileo Galilei in around 1610. And since then it has been existing like the whole time. So we actually don't know if it ever ceases to exist. But that's how Jupiter looks like when you look at it at optical wavelengths. What people back then did not really know was that it is actually also a great radio emitter. So this is how Jupiter looks like at radio wavelengths. Looks kind of like weird, I think, when you look at it for the very first time. So you see still Jupiter, and then you see these kind of like weird lobes. We call these lobes here. So that's a pure radio picture, nothing combined, no composite, nothing. And this radio emission from Jupiter was actually detected some time ago in 1955. And since then, we have observed Jupiter from, you can actually do this also from, with a small radio antenna from ground, because it's a very, very loud radio source in our solar system. So we actually studied this radio emission at different wavelengths within the radio spectrum. And we have been able to figure out that these lobes here that you see are actually generated by one of its moons, which is called Io. So Io is the moon that is nearest to Jupiter. And it is throwing materials because it's volcanically active and has volcanic eruptions on its surface. It's actually throwing material towards Jupiter that Jupiter picks up due to its very high magnetic field. And due to various particle acceleration processes, we also see radio emission from Jupiter being generated this way. So we call this Io torus. And this is just a sketch of how this is working. So Jupiter is here, the torus that Io produces, the torus of particles is here. And people did not know back then when Galileo was observing it that Jupiter can also be very well observed at radio wavelengths. And this is just a comparison when you observe Jupiter at various radio wavelengths, how much you do see. So you see when you change the wavelength from 13 centimeters to 22 centimeters, at some point Jupiter disappears and only the lobes remain. So they are actually the radio loud and not radioactive, but radio loud regions of Jupiter. And this looks kind of like a salamander. We know about this, so it looks kind of like strange a little bit. So when we have an optical picture and we this time make a composite with a radio picture, this is how Jupiter would look like. So here in the center, you see an optical image of Jupiter, and we overlapped it with these radio lobes. So these radio lobes, the color coding indicates where the radio emission is very intense. It's very intense in the reddish areas and not that intense in the greenish areas. So Jupiter has these so-called radiation belts, as we call them. What we also do in the case of Jupiter and in terms of multi-wavelength astronomy is to study all of the clouds. So the cloud structure, as you can take away from this picture, is kind of really complicated. So these storm systems are not easy to study, but what is also interesting about Jupiter is it doesn't seem to have like a solid surface, so nothing that you can walk on, but it seems to consist only of gas. So what we have been trying to understand as astronomers is how these storm systems, are being generated, and if they ever actually cease to exist. And you don't need to remember all of the belts here. This is just to show you how complicated Jupiter's atmosphere is in its details. But we are also using radio images and compare them with optical images. So the top picture is an optical image taken with the Hubble Space Telescope of the Great Red Spot. And the bottom picture is a radio image taken with the Very Large Array in New Mexico. And what people are trying to understand is how deep in the atmosphere is this Great Red Spot evolving? So where is it generated in which layer of the clouds? So this is something that we can also do with radio astronomy. We can actually look through the parts of the atmosphere that we cannot look through at optical wavelengths. And then we compare what we see at both wavelength ranges to actually understand what makes this Great Red Spot work? What makes it tick? Why doesn't it disappear like any big hurricane here on Earth, for instance? Well, one main reason is because Jupiter doesn't have a solid surface. So for instance, no mountains to, stop all of the clouds at. So this is one thing that you can do with multi-wavelength astronomy, dive into the atmosphere of a planet and try to understand how it works. Most recently, we have been also observing Jupiter at infrared wavelengths. So this is an infrared picture, and that's again an optical picture. And I put these next to each other because I wanted to show you that infrared emission is basically heat that we can observe with our telescopes from a planet like Jupiter. And you see that everywhere where these bands in its atmosphere are kind of like more bright, these are the areas which are more warm than the surrounding areas. And what we are trying to understand is basically in what depths are these clouds that we see. So these beautiful cloud structures, where are they evolving? Are they evolving high above the surface? Are they evolving in a couple of miles somewhere within the gas surface? So we really try also with infrared images to understand how deep are these clouds? How big are they? How much do they extend into the atmosphere? So we are trying to understand the weather pretty much on this planet. Yeah, and that's just one more example that I have. So sometimes there are new features showing up in these cloud structures. So this is, again, a picture of Jupiter, but not as a sphere, but basically just as a map. And you see that there was like a small eruption in the cloud structure, which we actually saw here, and we don't really seem to see it at infrared wavelengths, which is also an indication how deep in the structure of this cloud band here the eruption might have taken place. So lots of things that you can do when you observe an object at different wavelengths. And then, of course, we don't only have planets, but we also have nebulae. I have no time at all to go into details and all of these nebulae, but I just wanted to show you how diverse and how beautiful different nebulae can be in the universe. One nebula that I've been studying a lot, though, that I would like to talk about for a moment is actually the Crab Nebula. And does this work? Yeah. And that's a short movie, so the images will change in a moment. So this is how this nebula, which is called the Crab Nebula, looks actually at radio wavelengths. This is how it looks at infrared wavelengths. It's also color-coded, so the different colors are normal. And then you will see in a moment how it looks at optical wavelengths. And please pay attention to the fact that there is always like a slightly different shape depending on at which wavelength you are looking at. This is how it looks at ultraviolet, so it looks much smaller in the end. This is how it looks at X-rays. So at X-rays, we really see the heart of the nebula, as it seems. And these are all single pictures like that were taken. And when you combine all of that, you get this beautiful picture. So this is the Crab Nebula from its multi-wavelength perspective, when you look at it at different wavelengths and combine all of these pictures together. So make a so-called composite, as we call this. And the Crab Nebula is also a very famous multi-wavelength emitter. We've been studying it a lot. We still try to understand how the dynamics of this nebula work, because this whole nebula is nothing more than the remnant coming from a supernova explosion, some from a dying star. And the moderators should tell me how much time I have, because I could talk about this forever. So just cut me off at some point when you think my time is up, okay? So this Crab Nebula also shows flares at gamma rays, and I just wanted to share this information here with you because these flares have been so far only observed at gamma rays. So these are actually two pictures that are coming from a gamma ray satellite, which is called Fermi. And what we see is the Crab Nebula here as a dot. So it's not such a beautiful picture like the one that you just saw. When there is no flare. So this is the picture of the Crab Nebula when there is no flare. And then we saw it flaring up, so having like a gigantic outburst of energy at gamma rays in April 2011, and then it became much brighter. So we still have no idea what triggers these flares. We have some ideas, but we still need to gather more data. So this nebula, as beautiful as it looks on this picture here, is by far not stable. It also has these outbursts of energy, and we have no idea where they are coming from. But to learn more about it, where this emission is coming from, people are really zooming deep into the Crab Nebula. So this is the Crab Nebula around the center, which is the pulsar, and I will come to this in a moment, what this is. And basically, these two pictures to the left are optical pictures taken with Hubble. And these two pictures to the right are X-ray pictures taken with Chandra. So you see that we actually look into the nebula at two different wavelengths, at least, because we really want to understand where are these flares coming from. And the current assumption is that they are actually evolving nearby this structure here, which we call the Enlil region. But that's also something that you can do with multi-wavelength astronomy. We call this, we usually call this a morphological study.
We have just a couple more minutes, sorry.
Yeah, that's fine. I will just jump over. So I basically said everything that I wanted to say here. So let me just jump over to this one. So the Crab Nebula is a great example for many things. One thing is, though, that, as I emphasized already, it's a multi-wavelength emitter. So we study it at different wavelengths. Here you have an ultraviolet image of it. Here you have a radio and optical image of it. The radio parts are reddish. The reddish parts are the optical emission, and the other parts are actually the radio emission. We just compare basically what we do see in these two pictures. And we really are trying to find differences and commonalities to understand what are the dynamics of such a nebula, like the Crab Nebula. And same for the center. So this is the heart, once again, of the Crab Nebula. And you see here such a torus-like structure, which is caused by a star that we call the Crab Pulsar. And I will very briefly cover it in about 20 seconds from now on. But we also want to understand how the pulsar interacts, how the star interacts with the nebula. So we are comparing like X-ray images. So this is an X-ray image with radio and X-ray combined images, and we can see the same structures and also differences in the structures. So all of this is super interesting, and feel free to ask me questions if you have any. So in the center of this nebula, and this is my last point for today, is also the Crab Pulsar, which is a star that is here in the center. And a pulsar is nothing more than a very quickly rotating and highly magnetized star. So when you observe it at optical wavelengths, you see that sometimes it's there, like the second star, and then it's vanishing again. So it shows us its emission at a frequency of about 30 hertz, so 30 times per second. And this is pretty much how this works. This is just a toy model. So a pulsar is here. These are its radio emission beams. And when one of these beams, like in the case of a lighthouse, crosses our line of sight, we see actually a spike in the emission. And in the case of this particular Crab Nebula pulsar, we have also seen these beams at all kinds of wavelengths: radio, optical, X-rays, gamma rays. So we can do lots and lots of interesting multi-wavelength studies with this star. And yeah, with this, I'm coming to my summary. I know this was a lot of information at once, so feel free to ask me any questions. So basically, we are really trying to understand how a celestial source like Jupiter, like the Crab Nebula, like a star, how they generate the emission that we see from them. So what makes them work, what makes them shine. And we are really trying to understand the physics behind it. And I think this is a super exciting research field. So thank you very much. And I'm happy to take any questions.
Thank you so much for sharing. Kate and I are actually both in a class with Natalia's on this very subject. So it's fun to see the crash course side of things.
Yeah.
As you just mentioned, feel free to use the Q&A feature if you have any questions, and we'll try to get to them when time allows. But also we have a dedicated Ask an Astronomer section at the end of the night where we'll be taking open questions. So with that, why don't we move to Strawbridge Observatory and join Nathan.
Hi, I'm Nathan Walheis. I am a senior astrophysics major, and here with me.
Hi, I'm Julian. I'm a senior physics astronomy double major.
And yeah, we're going to be showing you around our telescopes that we have on campus. We're going to hold the laptop and hope that my hands don't drop it as they're prone to doing. This is our 16-inch telescope, and here around us, I'll try to move a little more slowly so I don't get anyone motion sick. Here's the telescope again. It is a 16-inch reflection-based telescope. And as you can see, it is very sort of short and stout, very different from the sort of like Pirate Spyglass telescopes that you may like normally think about. And those are refraction-based telescopes. We do actually have one downstairs, but it's not in use anymore. The reason is because this is much, much better, generally speaking. It is both much shorter, which allows it for it to be much more maneuverable. We're not having to worry about it like decapitating someone every time it sort of swings around, so that's a definite plus. And how it works is also fundamentally different and actually gives us like clearer images than you would expect to get from a refraction-based telescope. So how it works is light comes in from here, which is like the sort of opening aperture, and down way below, down there, right in this region, there is a mirror. This mirror is hyperbolic and sort of bounces all the light right back up again to here, where there is another mirror, this one time parabolic, that sort of collects all that light and shoots it down into, you guessed it, another mirror. That mirror is what sends the light into your eyepiece and lets you see it and stuff. And you might be thinking, geez, Nathan, why the heck do we go through all the trouble of all those mirrors? And it's because it lets us get the light very concentrated and focused in one spot, gives us very clear images, much clearer compared to your eyeball, which will be discussed soon, hint, hint. And it helps us sort of like deal with this annoying little phenomenon called chromatic aberration, which is a very fancy way of saying kind of like color weirdness, essentially is like in non-fancy-nese. And what that is so different frequencies and wavelengths of light actually sort of refract and move through media at different rates as soon as it interacts with like some sort of reflective or refractive surface. And that's like the same sort of reason why like you get a rainbow, or like whenever light shines through water or like a prism or something, you get like these rainbow shapes. That's because of chromatic aberration. And while that is very pretty and nice to look at, it's not very good for when you're trying to take science images. Or just like look at a planet through the eyepiece. It's kind of annoying really quickly. And yeah, this helps us deal with that. It's essentially better in most every way, except for it is mirror-based, so we will never be able to see the space vampires coming at us. We'll have no clue. I can't hear anyone laughing, so that is because of the format that we're doing this, but normally that gets a little giggle. You'll just have to take my word for it. Julian, is there anything else you want to say?
Yeah, so building off that, I'm going to point out that right now we actually don't have an eyepiece attached to this telescope. We have this box here, which is actually basically a fancy camera, like the kind of camera you might have on your phone, for example. It's just a bigger and more fancy one for science images. And then this wheel here has different filters on it that circle around and let us take different, like they're all optical, but multi-wavelength images that Natalia was just talking about.
I think we have some infrared and some ultraviolet.
Sure.
But yeah.
But yeah. So also the Nathan was talking about how this telescope is much smaller because much smaller than like the older ones. And the dome is actually older and was built when we were still using the older telescopes. And so we're actually standing on a platform right now because the telescope was built for a bigger telescope, and then they had to raise this one so it would fit. We could see out the big dome.
Yeah. So now, guess what? We're going to head over to the other telescope, which is very, very similar, but very much, not that much smaller. It's smaller. It's like appreciably smaller. So on our little adventure, ooh, it's raining a little. Good thing we have the dome. And here we are in a smaller dome. You might not be able to appreciate how much smaller it is, but it is significantly smaller. And we have our much more adorable 12-inch telescope, which, while like decently big compared to like general hobbyist telescopes, is fairly is noticeably smaller than our 16-inch. It's also easier to use, but it's the same sort of telescope. It functions in the same way. It's just the diameter is about 3/4 of the size, which translates roughly to 9/16 of the resolution, I believe, neglecting to take into account the eyepiece shenanigans and whatnot. But this one normally does have an eyepiece. We did not set it up for tonight because it is all like rainy and cloudy and stuff. But this is the one that we normally use for when we want to like actually do observing with the public, and we'll like point at planets and the moon and stuff, and it's very pretty.
Take his word for it.
Yeah, you'll just have to take my word for it. Yeah, you'll also have to take my word for it that being in the dome is really cool, and it actually has the phenomenon due to like the fact that it's spherical shaped, right? The acoustics actually have several node points that you can speak, and you'll be able to like whisper to someone across the room and they'll be able to hear it right as if it's in their ear. People can occasionally find it very creepy when I just like, they're being really loud and I'm like, hey you guys, can you quiet down? I'm not sure if you heard that, but I whispered, hey you guys, can you quiet down? And they hear it right in their ear, and it causes them to be quiet and be more respectful to the other guests in the dome. But yeah, it's cool. Is there anything else you think we should share?
The other fun thing about the dome is that there's a door. Maybe you can't tell, but there's this door in the dome that opens so we can see the sky, and we can spin the dome so that we can point at whatever area of the sky that we want.
Yeah. And the cool thing about
it also makes a lot of noise when you do that.
Yeah. Do we want to do that? Sure. The other fun thing is you may see this pulley. Well, you probably can't hear me very well right now, so wait. But yeah, it moves. It's cool. And yeah. The other cool thing is that pulley, just like the other one, is one that you have to pull by hand. And that one, unlike the other one, is feistier. And it will fight you when you're trying to open the dome. But that is okay because it builds character and stuff. And also because we're all college students and college faculty, and we're all a little too busy with other stuff to try to actually figure out a better solution. But yeah, it's fun. It's not that bad. I'm just sort of like having fun with the description. I believe we are ready to pass the torch on to the next presenter. Unless you think of anything else. No. Good.
Great. Thanks so much. Yeah, if anybody has, sorry. Good. Yeah, if anybody wants to learn anything about how the domes work, telescopes work, or what we use them for, feel free to ask at the end. But next up, we're going to move on to Sam. As Nathan alluded to, we're going to learn a little bit about humans seeing.
Yeah, I feel like Julia, Nathan's, and Natalia's presentations were all perfect for this. So let me transition smoothly, hopefully. Okay, yes. All right, so I'm going to talk about our eyes and comparing them to the telescopes. Kind of to the ones that we just saw, but I'll probably be using a more specific example. Again, my name is Samantha Berry. I go to Bryn Mawr College and I'm a junior, and a lot of the information that I'm going to use for this presentation is adapted from an instruction like learning tutorial from the Harvard-Smithsonian Center for Astrophysics, and they have a ton of informational things that I'll also plug at the end. But I had to mention that because a lot of this comes from their work. So first we're going to start off in thinking in what ways physically are telescopes different like our eyes? Because you'll find that they have some very similar characteristics, and you can kind of look at this visual down here to maybe see a couple of things that look similar, but I'll also tell them to you. To start, both focus the light in some way to form an image. The eye uses the lens and the telescope uses a set of mirrors. This is a more basic layout than what Nathan just showed us with our telescopes. So they focus both here at the focal point of the telescope and then in our lens in the eye here. And then similarly, both eyes and telescopes have some sort of light detector to sense the image they are receiving. So the eye has the retina, which is all in like the back of this area right here, and that contains about 1 million cells that are very sensitive to light. And then some telescopes contain a silicone chip, a CCD detector that contains roughly 1 million individual wells that are very sensitive to light as well. And that sounds fancy, but those telescopes just work like a digital camera where that chip will record the images as a picture file. And I think that's kind of what Nathan showed on the 16-inch that we have. And then lastly, to make all those above things work, what both telescopes and eyes need is an opening. So you'll see an opening for both. So now I want to talk about 5 comparisons, and this is basically the beef of this short presentation. So comparison number 1 is the size of that necessary opening. We have pupils, which is the opening to the iris. I apologize for this intense image, but it gets the point across. And that is through which light passes before reaching the lens, and then it gets focused into the retina. And then for telescopes, they have aperture, which I think Nathan also mentioned, which is the diameter. So like you have the circular lens of your telescope, and the diameter is a length from top to bottom, or just one side to the other. So the viewing area of these two things, the pupil and the aperture, are very important. So if you just think about the diameter, a pupil is about, because it changes, 1/4 of an inch wide. And an aperture, the telescope I'm going to use for example is 6 inches, but like we just learned at Strawbridge, we have a 12-inch and 16-inch. But if we're looking at a 16-inch, the aperture already is 24 times wider than the pupil, but area comes in all over it, light comes in all over the area. So if you compare the two areas of the pupil and the aperture, the telescope actually is 576 times as much as a pupil, which means the telescope gathers that much more light, which is super important, and it enables telescopes to gather much more light than the eye, so it can detect fainter objects than the unaided eye. And then the second comparison is exposure time. So throughout this presentation, again, it's from the Harvard-Smithsonian like web page, and they use this micro observatory setup, which is basically just several 3 feet tall, 6-inch reflecting telescopes in Cambridge and Arizona. And these are the ones with like the silicone chip I mentioned. So for these guys, they have an exposure time, and that's a shutter speed from, you can pick 0.05 seconds to 60 seconds. And exposures longer than 60 seconds are not allowed with these telescopes because the image is often blurred due to vibrations and other factors affecting the telescopes. Unlike the Hubble, which was mentioned earlier, which is free from those vibrations as it's in space, so it can have long, hour-long exposures and give beautiful pictures. But the human eye has no shutter and does not have a kind of exposure time, but we do have reaction time. So about every 1/15 of a second, our eyes send our brain an image. And that is roughly the time it takes the nerve cells in our eyes and optical nerves to gather light, fire, conduct an electric signal to the brain, and then prepare themselves for the next round. So like just over and over again. And then, you know, a fun thing to do is that you can measure your reaction time with like somebody if you drop like a pen and you try to catch it. Yeah, humans aren't that fast. So, for example, a very faint object like distant galaxies need long observation times. 60 seconds for a telescope is about 900 times longer than the exposure of the human eye. And then these pictures over here are the little micro observatory things, telescopes, that will come up again in this talk. So the next comparison is sharpness of vision. And this is a fun topic because, as you can see, I am wearing glasses, and this is something I do not do very well. But it's best to explain this with an experiment that you can do. And so if you are with like a partner or somebody and you're in a really long room or a driveway or something like that, and somebody holds the Harvard instruction thing, it's an aluminum foil with 2 holes punched in it, about 1/8 of an inch apart from each other. But if someone holds a paper with like 2 holes punched in nearby each other and then a flashlight in between, there will be a distance that when you look at it, it will only look like one light source, even though there's 2 holes punched. And as you walk closer, you will see that it starts to become the 2, which it actually is. You can differentiate the 2. And that is called the point at which you can resolve the 2 objects. And for humans with good eyesight, that's about 35 feet away. In comparison, we have the micro observatory little telescopes again, and they can resolve a point of light that is 1/8 of an inch apart, 2 points, from about 875 feet away, so 25 times further. Very much better than humans, but necessary when you think of like 2 stars or 2 opposite objects very close to each other in the sky. And then the 4th field of view, we have 5, so this is the second to last one. The 4th comparison is the field of view, and this is where we humans have a leg up. So this picture right here, like if a human is at a beach, they could take in this entire picture, which is more than 90 degrees. And then again, with our example telescope, the micro observatory, their main camera has a finder view of 10 degrees. So that's like this little black box, and that's what they use, you know, to see multiple different objects that they might want to focus on. And then once they focus on an object, they use the main camera, which has a field of view of only 1 degree, so very tiny. And so having a wide field of view is a survival advantage for humans. We can quickly react to animals or moving cars. But of course, telescopes usually are designed to focus on the small objects in the sky, so this comparison works. And you can measure your field of view by looking straight ahead and outstretching one arm, and while wiggling your thumb, moving your arm slowly behind you. And when you stop, when you can no longer see your thumb wiggling, and then you do it with the other arm, and then you'll get like this kind of pretty wide wingspan. And this is usually for an average human about 150 degrees, which is quite a big field of view if you think about it. So there's that. And then the last comparison is color versus black and white. And this is extra interesting because I don't know if you know, but I knew that humans had a good peripheral, but I didn't realize that we have much more restricted field of view for seeing color than seeing shapes. And so you can do that same experiment again with your arms, but instead of moving your thumb, holding a bright red credit card or something, and you will not be able to have your arms as wide as you did before you stop seeing that red credit card. Your brain will stop seeing light at a smaller angle, or it stops seeing color, a smaller angle than you stop seeing movement, which is super interesting. The reason why this is because the color sensing cells are concentrated in the central part of the retina, which, if you remember, it's like the retina is this back part of the eye, and then the central bit is just this tiny area. And then those color sensing cells are called the cones, and they do not function in low light. So that's like another disadvantage we have. We can't really differentiate color and darkness. Now, in comparing that to our example telescope, the microobservatory with the silicone chip, it actually only really sees in black and white, which is its measurement of brightness of light. So it sees that it's really bright over here and dark over here. But then, like Julian pointed out, it has these filters for the humans to see the actual color. So we have this example image here of the red, green, and blue filters of this man. And once you put it all together, it gives you the true color image. And so that is my conclusion of like the examples of how our eyes compare to telescopes. Obviously, telescopes are much more superior than eyes, but they were built by humans to help us, so it's really great that they're better. And then I just want to plug again this Harvard Smithsonian Center for Astrophysics. Like, if you just Google that and go to their resources, and for educators and students, they have tons of more like instructions for fun activities like this. And that microobservatory, you can actually request remotely an observation, and it'll be emailed to you, which I did do. And I shared with everybody that's on the panel today, and it turned out to be black, but you might actually get a good observation. So I implore everybody to look into more of that. And that concludes my quick rundown of eyes versus telescopes.
Great, thank you so much. That was so interesting. I think, yeah, we're going to move on to a little interactive quiz. Can test out your astro knowledge, some stuff that we learned tonight, some stuff that is relevant. Hopefully we'll learn some things along the way. So I'm just going to put a link into chat that everybody can go to. One moment. And I'll try to share my screen. Hopefully this works. There we go. So if you put this pin in at the link, you should be able to join into the quiz. And once some people are in, we can get started. And if any of the other panelists want to comment on anything after the questions, feel free to go ahead. So just wait a minute or two. In the meantime, if anybody has any questions immediately, again, feel free to ask in the Q&A. We can try to get through those. And then, yeah, after this, we'll be doing our Ask an Astronomer section. So great. Not a panelist is here.
So just for an example, I just went on my phone to like any internet app and just typed in www.kahoot.it, and then you just type in the pin and I'll get you right to it.
Before we start, I'll say I have one quick fun fact about something Sam mentioned on, I think, the second to last slide that's very interesting, about being able to see black and white more on your peripherals. If you're ever wanting to look at something in the sky, a certain constellation or a certain object, and the sky isn't quite dark enough to see it when you look directly at it, try looking at it out of the side of your eye. It's a technique called averted vision. And it's kind of shocking at first, but there's a lot more that you can actually see than it might initially appear. So. Why don't we give it another 30 seconds and we'll get started? Good. Okay, I'm gonna start it. If you also want to join in at any point, I think the code should still work even when it's happening, so. So our first question, our galaxy is called the blank and the nearest large galaxy is called blank. So it's a double question. Yes. So yeah, both of those two options at the top are correct. That image that we just had up is a picture of Andromeda, our nearest large neighbor. And in some astronomical terms, you might call it M31. And that means that it's the 31st object in the Messier catalog. So let's move on to the next question. Which of the following is the largest? We've got the Earth, the solar system, the local group, and the universe. Awesome, yes. Yeah, the universe is the largest of these options. One that I think people might not necessarily have heard of is the local group, and that refers to the group of galaxies that the Milky Way and Andromeda is in, as well as some of our other neighbors. All right, so relevant to recent stuff, what part of the spectrum, that's the spectrum of light, the electromagnetic spectrum, can the human eye see? We have visible, infrared, radio, and X-ray. Yes, correct, visible. I would love it if the others were true as well, but as Sam said, that's why we build devices to do that for us. So which of these can you not see from the Earth's surface? We have radio, visible, gamma rays, or the ground. I should specify, not see if they're coming from space. Yeah, so I'd say generally you can see the ground on the surface of the Earth. But if you're looking up, then I guess the answer is no. Yeah, gamma rays, as we see in this, it might not be immediately apparent, but what this is showing is how well different parts of the spectrum make it through the atmosphere. So because of the nature of the molecules of gas that we have in our atmosphere, certain types of light are just blocked or they're let through. So we see here, this really big valley on the right is all radio, and that has a super easy time passing through our atmosphere. But the higher energy light, such as gamma rays on the left, gets stopped and absorbed by the oxygen and nitrogen, I believe. So this is a bit of a follow-up question. Why don't we build gamma ray telescopes on the surface of Earth? Yeah, so as we said, the atmosphere stops gamma rays from coming through when they come from all the different types of astrophysical sources that generate them, which is also good for us. I don't think gamma rays are great to be standing around and bathing in. Okay, this one is a bit tricky. How large is the largest telescope that we've constructed on Earth, I should say? So our options are 16 inches, thousands of miles, 40 meters, or 2 parsecs. As a little hint, a parsec is about 3 light years. Yeah, so this is a tricky one. And I'll admit that the phrasing might be a little deceptive. So 40 meters is about the scale of the largest optical telescopes that we can build on Earth at the moment. That's what we think of when we imagine a telescope, a big mirror dish. However, there's a trick in things like radio astronomy called aperture synthesis. What that means is if you have 2 radio telescopes, which are big dishes, and they're 10 miles apart, they behave like they are one big 10-mile telescope. So if you remember, it was in the news recently, or at least in the past couple of years now, I guess, there was this beautiful image of a black hole at the center of the galaxy M87. And that was taken with something called the Event Horizon Telescope. And what that actually is an array of telescopes all across the Earth that came together to make one telescope with the effective size of the Earth, basically. This is a technique called interferometry. Okay, so the wavelength of microwave radiation is similar to this one. Stuff we haven't said exactly what this one is, but we have a whale, an elephant, bacteria, or cat for different orders of magnitude of scale, I suppose. Maybe a whale and an elephant are almost the same size. Whales are bigger. Yeah, so this is a tough one. And maybe I shouldn't have put it in because we didn't really go over exactly this one particular part of the spectrum. But microwave radiation is generally between 1 millimeter, so about the space between my fingers right now, up to a meter, which is about 3 feet. So it's not necessarily intuitive because it's called micro, and there are a lot more micro. In fact, it's not even on the scale of micrometers. So that just dawned on me. But yeah, let's see. So true or false? I should say, in general, electromagnetic radiation travels at the speed of light. Yeah, so this is generally true in the sense that if you have light moving through space, it will travel at the speed of light. One really good thing to point out here is that when we talk about light, we are talking about electromagnetic radiation. So it might be tempting to think of them as 2 separate worlds of things, but all light that we see and all light that we observe with our telescopes is part of the same electromagnetic spectrum. And I'll note the technicality that I alluded to, which is sometimes if you're shooting light through something, it can slow down a little bit, but it's still very fast. So, similar vein, particles of light are called electrons, neutrons, photons, or lightons. Yeah, that's a good one. Yeah, photons are what we call the particles that carry light or behave as light. Electrons, neutrons are things that we find in atoms. Lightons are something that I made up, though it would be fun if they were real. Let's see. So this is a bit of a callback. What are we looking at here? Our options are the Eagle Nebula, the Crab Nebula, a supernova, or a Petri dish. Yeah, so this is the Crab Nebula. For anybody who said supernova, that is definitely a reasonable answer. The Crab Nebula is a remnant of a supernova. So a supernova is kind of the event itself when these massive stars die and shoot off all this material that creates these beautiful nebulae. All right, last question, true or false? Haverford's astronomers use multi-wavelength astronomy. Yeah, so this one is true. I think it's kind of relevant to mention here, just in that multi-wavelength astronomy is incredibly versatile. And maybe even if you're an astronomer, an astrophysicist who works and specializes in one part of the spectrum, your research and your work is always going to be interacting with a more composite, rounded view that comes from looking at all the light that we have available to us. So that's all that we have for the quiz. But we're going to go straight into Ask an Astronomer now. So if anybody has any questions about anything they heard tonight, anything they want to learn about us, about astrophysics, about Haverford's astronomy program, feel free to ask. You can put your questions in the Q&A. Let's see, yeah.
I think I have a question for Natalia. I might be studying pulsars this summer with Andrea, and the pulsar, was it in the Crab Nebula? I didn't understand why it showed 2 spots and then 1 spot during one of those visuals that you had.
Oh yeah, this was an optical image made via Lucky Imaging, so very, very quick CCD, basically imaging. And one of these dots was the Crab pulsar, and since we can also see that optical wavelengths, you see it basically 30 times per second. So there are moments when you don't see it. So it's kind of like fast for our eyes, but for this Lucky Imaging technique, it's actually it works pretty well to actually see like when it's there and when it's not there. So there is a star nearby as well, and that's why you'll see 2 dots.
Got it. Thank you.
Sure.
So we have a couple of questions in chat. Start with the astrophysics question. So can you tell us more about how the Crab Nebula formed? Anybody would like to field that?
Do you want me to chime in on that?
Sure, go ahead.
Okay, so this was so the Crab Nebula was formerly like a very high mass star. So when we talk about high mass stars, we say usually these are stars with at least 8 times the solar mass. So much bigger than our sun and more heavy. And each star is stable just because it's converting hydrogen into helium and heavier elements in its core. But at some point, this hydrogen is used up, and also helium and many of the other more complex elements. And when this happens, then the gravity that is acting on this star is trying to contract it. And if there is no nuclear fusion, as we call this whole process happening, then there is like an imbalance between the gravitational pressure acting from outside on the star and the gas pressure acting from the inside. Now, from the inside out in the star. So the star starts to shrink. And at some point, via various chemical interactions, which I'm happy to talk about more if I would have more time, this whole procedure, this imbalance leads to a supernova explosion. And it basically, we call it also core collapse supernova, which means that the whole core is contracted so much of the star when the star is not doing nuclear fusion in its core anymore, and gravity takes over, that at some point the core collapses into it. So this is actually something that I'm always having fun explaining. So if people have more detailed questions, please go ahead. But essentially, the Crab Nebula formed via such a supernova explosion, and it has these beautiful shapes and forms. If you don't see a Crab Nebula in there, a crab in it, it's fine. I don't see it either, but the people who discovered it saw it. And so they called it like that. But all of these shapes are basically the interior of the former progenitor star before it collapsed. I hope this was understandable.
Great, thanks so much. We have another question. I think potentially difficult to answer. Karen might be the most fit. Do you guys have any idea when the public will be allowed in the observatory again? Seems really cool and like to visit.
Yeah, in terms of external visitors, we have to be guided by the administration's rules. And right now, visitors are not permitted on campus except for special exceptions. The plans for the fall semester are that things will be much more back to normal. Things are moving in the right direction. If everyone out there is vaccinated and we reach herd immunity, it'll be much more likely that we can bring people in for in-person public observing, and we'd all like to do that, I know. So let's keep our fingers crossed and hope for not too long in the future. For students on campus, the answer is a little different. We might be able to do something for students and for the campus community, as long as it's small and socially distanced, much sooner.
I suppose if we're waiting for other questions, I can pose a question. It might be difficult, or I understand if there's not, you don't have an immediate answer. But just given the theme of the night, does anybody have a favorite part of the electromagnetic spectrum from an astrophysics perspective, or not an astrophysics perspective? As an open question to anybody.
Favorite spectral lines? So different atoms or molecules emit very specific lines. I've got two favorites. The H1 line is 21 centimeter radio emission line. That's a great one. But I'm also pretty fond of H alpha, hydrogen alpha, which is an emission line of ionized hydrogen. I'm bad at numbers, but there's a highway in New Mexico that has, the number of the highway is the wavelength of the emission line in angstroms.
That's a cool fun fact.
I think I'll cheat with like multi-messenger, using multiple wavelengths and things to look at astronomical objects and say gravitational waves, and like how when we pinpoint like a source of a gravitational wave like LIGO or like other detectors, looking at it really fast with like observational telescopes and seeing if there's anything radio happening in the radio waves or visible or ultraviolet. I think that's really cool. So
those are the astronomers with alerts on their phones, and they have to observe now, quick. Cool. Anyway, so pretty fun.
And if people don't know, like astronomers have to queue in telescopes, and like sometimes I think they can bump up if like an event like that happens.
Oh, yeah, that's happened to me when I've been observing, that someone had a program that was approved for unusual events and something seemed like it was happening, and so we were told we had to observe their source, not ours. And then it turned out nothing interesting had happened, but I suppose it was worth a go, worth a try.
You very often seem to do this with gamma ray bursts when they start coming. Then there's with the SWIFT monitoring program, as we call it. And I was once observing when out of a sudden the telescope just started moving without me doing anything. And I was kind of like, what's happening? So, and then I got the alert. So I was kind of like, okay. So,
I mean, the level of automation that telescopes have varies, right? Some are very hands-on, like ours are not connected to the internet. You can't point them remotely. You have to be there, and a lot of professional telescopes are that way too. But increasingly, we are seeing telescope facilities that you can observe with remotely, and they will have staff there for maintenance. But what is the word? It's Friday. It's late. The signals that tell them where to point come remotely from possibly a long way away.
I think gamma rays are cool because you can get turned into the Hulk if Marvel has taught us anything with their science. Actually, no, it would kill you probably almost immediately, as well as most other things on this planet if they actually came into contact.
Nathan with all the non-facts this evening. Although I do think comparing cats to microwaves is the worst one. But anyway.
That's on me. I will take that.
That's okay. Those microscopic cats, they get you every time.
Well, definitely neutron stars, but neutron stars all over. So I don't have a preferred field. I'm currently learning about infrared. But the more I learn, the more questions I have, which is pretty much normal in research. But yeah, it's neutron stars over the whole electromagnetic spectrum.
So we have another question. This is a good one. What units are wavelengths measured in for multiple different things? I'm wondering if anybody would like to take that.
So angstroms are a pretty common one. And angstrom is like 1/10⁻10 meters. It's generally denoted by like the, I don't know what
the A with the little circle on top, but just to clarify, wavelength is a length, so it's measured in lengths. And angstroms are a good one because most particularly visible wavelengths are small. So angstroms end up being a good unit for that. But for example, radio waves are big, longer. And Karen mentioned the H1 line, which is 21 centimeters, which would be a lot of angstroms. So
there's a big range in scales, right? From gamma rays, which are ridiculously tiny, to, meter wavelength radio waves. So any length scale. But then astronomers are pretty naughty, and sometimes we'll just drop into like using frequency instead, because wavelengths and frequency there's an equation that relates them that just has the speed of light in there. So sometimes we just jump in and talk about frequencies instead of wavelengths.
I found also that sometimes high energy astrophysicists will skip the entire thing and go straight to referring to the light in just the energy that it has.
Oh, yeah.
Yeah. Well, that works too, because you just got the Planck constant and the frequency. So it's all constants. I mean, in theory, it's just set everything to 1 anyway. But
I was going to say it depends pretty much upon the community. So gamma ray astronomers use electron volts or energies. Radio astronomers use meters, centimeters, whatnot, same as optical people. Then we have the X-ray people. And I noticed when you read old papers, then you also have differences in the units between CGS and SI. Yeah. So you need to pay attention to that.
Well, we all agree units are important. We just don't agree which units are the ones that you should use.
That's certainly true, yeah.
Yeah.
James uses cats per millimeter long cats.
So I suppose, I don't know how we're doing on time, but we can keep questions open for a little bit more. I think otherwise we're coming close to the end of the program for the night. Yeah, I'll let the forum open though still, just for a bit more.
I feel the need to disagree with myself and say microwaves apparently can go up to 30 centimeters, which might have been the point we're making. That's a reasonable scale for a cat.
I read, yeah, I saw on the, I must have misread. I was going for order of magnitude and saw millimeter, 2 meter, but I suppose if it's just 30 centimeters.
I think I was thinking millimeters, and I was thinking teeny, teeny, tiny cats running around.
So we can have neutral hydrogen as the like 0.68 cat line.
Yeah, absolutely. Good unit there.
Yeah. Okay, we have another question. What are your favorite objects in the sky? Mine is the pillar of creation.
That's a beautiful one. Here it's definitely the crab object that I will probably study till the end of my days, because it's really a cool object.
My favorite, and it's partially for astrophysical reasons, but also because I think it just looks the coolest, it's M51. It's also called the Whirlpool Galaxy. Definitely go Google it. It is a beautiful spiral galaxy that is interacting with another small elliptical dwarf galaxy. And so there's this gravitational pull going on between the two, and this other little galaxy is just kind of almost pulling on one of the arms and trailing off, and it's really stunning. So that's definitely my favorite.
I said it last time, so I guess I feel like I'm committed to this. The Pleiades star cluster is currently still my favorite, just because it's so easy to see and it's like so friendly in the sky. Just like, oh, hey, that's where it is. I see it all the time.
I have so many different, I've been like, what do I want to pick? But I'm going to go with Saturn in a shocking turn of events, but partly because it's one of those objects that when you actually first get to look at it through a telescope, it's not uncommon that people's reaction is, that's made up, right? That's not real. It actually looks like you imagine. And I think that's pretty cool that you can look through a telescope and see that with your own eye. So I'm going with that one.
Guess I'll pick Orion just because that hasn't been said. That's a nice one. Got a lot of cool looking objects there, and Sirius is a interesting star, as depending on when you observe it, the atmosphere can cause the colors to shift like very rapidly from like orange to green, just over and over and over. And the first time I saw that, I was thinking like, what the heck is going on? I have no idea. And then I was like, wait, actually, we do have a bit of an idea. But it's cool. Do you have any favorites?
I don't know, since Karen didn't pick it in a shocking turn of events, I'm going to go with NGC 1300, which is a fun, it's a spiral galaxy with a really strong bar, which is just like it's like a bar in the middle, in between the dot at the point in the middle and where the spirals start. And it's NGC 1300 has a really strong bar, atomic bar, which is fun. And it's like sort of seems like it became the mascot of our research group, which is also fun. Yeah.
I might answer with whatever I've heard of most recently. And so I think that one of the nice things is that there's so many different things. And even among, say, deep sky objects, there's all kinds of different objects and different structures. And so I think that often, whatever I've heard of most recently becomes my favorite for a period of time until I hear of something else. And so I'm not sure that I can pick one, but it's like picking a favorite book, right? There's so many out there. How do you choose? And yeah, and so I think that that's going to be my non-answer answer.
Great. All right. Well, I think with that, we're going to wrap it up for the night. But thank you so much for coming. We really look forward to seeing you next semester, hopefully back in the observatory at some point soon. We can do some real hands-on observing. So yeah, thank you for coming.